Hello everyone. In today's class, we'll be looking at these two questions on the board. The first question is a question about ideal gas law, and the second question is a question that has to do with what we call specific heat capacity. Okay, so now the first question, we have the equation of state of an ideal gas is PV equals to nRT. Explain why the temperature must be measured in Kelvin. Yes, the temperature must be measured in Kelvin. That is because we know that ideal gas law is derived from the kinetic molecular theory. And the kinetic molecular theory relies on the relationship between the average kinetic energy of gas molecules and absolute temperature, because that's why we have what we call the postulate of kinetic theory of gas. We have, I think we have more than 5 postulates, but I used to remember that before now we used to have 5 postulates of kinetic theory of gas. Okay, now one of them is that gas consists of tiny molecules which are in constant random motion. That's the first postulate. The second postulate is the one that talks about the volume of gas molecules is negligible compared with the volume of the what containing vessel. Then the third postulate is the one that has to do with what we call elasticity. Okay, that is, now when we talk about elasticity, of course we know that the container will be a closed container, that is a closed system. So now the continuous bombardment of gas molecules with the wall of the containing vessel, all right, will give rise to pressure of gas. Okay, and that's why we have this equation PV equals to nRT. But now the postulate I want to explain here is the one that has to do with what? Elasticity. Okay, that is, molecules of gas collide elastically with each other and with the wall of the containing vessel. So the continuous bombardment of gas molecule, which is also one of the postulates of kinetic theory of gas, is that the continuous bombardment of gas molecules with the wall of the container of its containing vessel will give rise to the pressure of the gas. Then the volume occupied by gas molecules, okay, is negligible compared with the volume of the container. Then also we know that these molecules, okay, don't exert significant force on each other. Okay, there's no appreciable attraction between the molecules of gas. Okay, the attraction of one gas, okay, one mole of a gas with another is not they don't exert significant force. That is, it will not be felt exactly now. But it is only during collision. That is when they exert significant force. Okay, so which means it is during, now I said when they bombard the wall of the container, okay, the force exerted per unit cross-sectional area of the container will be equals to what? Pressure of the gas molecule. So like I said, that they don't exert significant force, of course, on each other, okay, except during collision. But the one which explained question 1, I mean the first question, is the one that talks about measurement of temperature, because we know that temperature measures the degree of warmth of a body. That is the degree of hotness or coldness of a body, which is the common or general definition for temperature. Or we can also define temperature as the measure of the molecular activities of the molecules of a substance. Okay, now then, apart from now, but that is what in that one will now be explained based on the 5th postulate. Okay, the 5th postulate is the one that talks about the average kinetic energy of gas molecules will be proportional to its what? Absolute temperature. So why is the temperature absolute? I just explained that the ideal gas law, okay, is derived from the kinetic molecular theory, which relies on the relationship between the average kinetic energy of gas molecule and absolute temperature. So the greater the average kinetic energy of the molecules of gas, okay, the higher the temperature. Okay, so which means that is that is the fast energetic molecules of gas which escape into the top space. Let's say in the case of liquid or water, for example, okay, they escape into the top space and they accumulate the top space in form of what? Bubbles of vapor. Okay, these bubbles of vapor. So the bubbles of vapor, okay, is as a result of the fast energetic molecules which escape into the top space of the what? Of the liquid, okay, in the container. So the fast energetic molecules is because there's what? We have that's the molecules acquire enough energy to be able to escape, into the top space of the liquid. So now, and that would be because the average kinetic energy of the molecules of gas is proportional to its what? Absolute temperature. So the Kelvin scale is an absolute temperature scale. That is the one we call thermodynamic scale temperature, because it starts at the what? 0 Kelvin. The 0 Kelvin represents the what? Absolute zero. Okay, where all molecular motion ceases. Okay, that is at absolute zero, which is 0 Kelvin. All molecular motion ceases. So for this reason, it is important, or it is a must, for temperature to be measured in Kelvin, so as to accurately reflect the relationship between the average kinetic energy of gas molecules, pressure of gas, volume of gas, okay, temperature, and also the number of moles of gas molecules. Yes, that's it. So, which means in this case, okay, now what we have here is that so to answer the first question, okay, so the first question, so we know that, so the temperature, let me put it this way, the temperature, okay, must be measured in Kelvin. Okay, must be measured in Kelvin, so as to accurately reflect the relationship between the average kinetic energy of gas molecules, pressure V, okay, pressure, okay, volume, pressure P, volume V, okay, and number of moles of gas. Number of moles of gas. So we can then conclude that. The absolute, or the Kelvin scale, is an absolute scale. Okay, is an absolute scale, meaning it starts at 0 Kelvin, okay, where all molecular motion ceases. This is the answer to the question. That is, temperature must be measured in Kelvin, because Kelvin scale is an absolute scale, meaning it starts at what? 0 Kelvin, where all molecular motion ceases. Or we can, yes, that's why I said the temperature must be measured in Kelvin, so as to accurately reflect the relationship between the average kinetic energy of gas molecules, pressure, volume, and number of moles of gas. That is because I said the ideal gas law, okay, is derived from what we call the kinetic molecular theory, which relies on the relationship between the average kinetic energy of gas molecules and absolute temperature. And that's the fifth postulate of kinetic theory. And that's the answer for question number 1. That's A. Now the second question. We have a cylindrical cup of internal diameter 7.0 centimeter and height 8.5 centimeter. Is filled to the top with water. The density of water is 100 kilogram per cubic meters. The mass of 1 mole of water is 18 grams. Then we have the specific heat capacity of water is 4,200 joules per kilogram per Kelvin. Show that the minimum time for a 0.50 kilowatt camping kettle to bring a cup of water at 20 degrees Celsius to boiling point is about 200 seconds. About 200 seconds, not exactly 200 seconds. Okay. So now what we need to do first, okay, is to calculate the volume of the cylindrical cup. Okay. Why is that? Why is it that? Now, because we are given the density of water, okay, and the cup hold water of certain, and that's it holds water, okay, it holds water, and the density of water is given, which is 1,000 kilogram per cubic meters, okay, but we are given the mass of 1 mole of water, which is 18 gram. I don't think this one is necessary, okay, but let's look at it this way. So the first thing is, now we are given a cup. We have a cylindrical cup, okay, we have a cylindrical cup. This is the cylindrical cup, okay, we have a cylindrical cup. Now, the internal diameter, di, is 7 centimeters. That's the internal diameter. Internal diameter is 7 centimeters. That's the internal diameter. Okay, now the height of the cup. The height of the cup is given to be 8.5 centimeters. The height of the cup is 8.5 centimeters. So now we know that to calculate the volume of cylinder, okay, to calculate the volume of cylinder, we will have to make use of, so volume, we make use of V equals to pi r square h. So volume of cylinder, which is V equals to pi r square h. So the internal diameter, which is given to be 7.0 centimeters, so the radius will be d over 2. 1/2 of a diameter is equals to radius. So which means we're going to have 7 divided by 2, which is 3.5 centimeter. That's the diameter. So we are given the height, which is 8.5, okay, 8.5 centimeters. So now all units must be converted to what? Into meter, into what? Meters, that's SI units. So let's convert this. The radius will become 0.035 meters. Then the height will become 0.085 meters. So the volume, so we have, then let's not forget that pi is 3.14. So we have 3.14. We are using the formula V equals to pi r square h. So 3.142 multiplied by 0.035 raised to the power of 2 multiplied by 0.085. Okay, so let's multiply. Now let's get the value of the volume. So the volume is 0.035 multiplied by 0.085. Okay, then also multiply by 0.035 because we have 0.035 squared. Then multiply by 3.142, which is the value of pi. So the volume is equals to 3.27272 times 10 raised to the power of minus 4 cubic meters. So this is the volume of the cylindrical cup. That's the volume of the cylindrical cup. Now, that's step 1. Okay, this is step 1. Step 1 is for us to what? Calculate is for us to calculate the volume of cup. That's the cylindrical cup. Let's manage the space. So now step 2. So step number 2. Now we need to calculate the mass of water, but the mass we are given here is what? Mass of 1 mole of water, which is 18 grams. So to calculate mass of water, water is H2O. Okay, so to calculate mass of water, we know that density, okay, density of water will be mass of water over what? Over volume. So the volume we just calculated. So then mass of water will be equals to density of water multiplied by volume. So that mass of water will be equals to density of water is 1000. Okay, we're giving density of water to be 1000 kilogram per cubic meters. Okay, so then we multiply that by the volume, which is 3.272 times 10 raised to the power of minus 4. So the unit of this will be in what? Kilograms. The unit will be in kilograms. Okay, so let's get the value for, so what is 1000 multiplied by? So this will be mass of water. Okay, mass of water will be, when this is multiplied, so we're going to have 0.3272 kilograms. This is mass of water. We just calculated mass of water. That is 3.272, okay, times, that's 10 raised to the power of 3 multiplied by 10 raised to the power of minus 4. That'll be 10 raised to the power of minus 1. So when multiplied by 3.272, okay, that will be 0.3272 kilograms. And that's the mass of water. That's step 2. So now step number 3. Step number 3 is for us to calculate the heat energy, okay, the heat energy required to raise water from 20 degrees Celsius, okay, to boiling point. So that's step number 3. Now step 3. Step 3 is to calculate the heat energy required to raise the temperature of water from 20 degrees Celsius to boiling point. Now we know that the boiling temperature of water is 100 degrees Celsius. So that means from 20 degrees, the temperature is raised to from 20 degrees to 100 degrees Celsius. So that means that we're going to use the formula Q equals to mass of water, okay, specific capacity of water multiplied by temperature difference. So we know that the initial temperature of water will be 20 degrees Celsius. Then the boiling temperature, okay, the boiling temperature is 100 degrees Celsius. And we know that the specific heat capacity of water is 4,200. So we have 4,200 joules per kilogram per Kelvin. Then, okay, I think that's fine. So the mass of water is what we just calculated here, and that's what? 0.3272 kilograms. So Q will be equals to 0.3272 multiplied by 4,200. That is this. Then 100 minus 20. That will be 80. Okay. So what is 4,200 multiplied by 80, then multiplied by 0.3272. Now that will be, so Q will be equals to 109,939.2 joules. Okay, 109,939.2 joules. That is the heat required, okay, to raise the temperature of water from 20 degrees Celsius to what? To boiling point. So step 4, which is the last one, okay. So remember, we want to show that the minimum time taken for 0.50 kilowatts camping kettle takes to bring, okay, a cup of water at 20 degrees Celsius to boiling point is about 200 seconds. About 200 seconds. So that means now we want to calculate the minimum time. Calculate the minimum time. The minimum time. So let's say that's T minimum. Now we know that energy is what? Is equals to power multiplied by time. So we have T minimum. Okay, and we can express T minimum in terms of Q. So we know that T minimum will be equals to Q over what? P. Now let's not forget that P is 0.5 kilowatts. 0.5 kilowatts. So we have our T minimum to be equals to this value 109939. 109939.2 joules over 0.5 times 10 raised to the power of 3. Remember, kilowatt hour. So the unit of time, this is in joules per seconds. Okay, the unit of time will be seconds in this case. So that joules will cancel joules. So what is this value divided by 0.5 times 1000 will be 500. Yeah, that will be 500. So divide by 500, that will be 219. So the minimum time taken is 219, okay, 0.9. So seconds. So when we approximate this, okay, to the nearest 100, okay, that will be 200, okay, that will be 200, that will be 200 seconds. That is to the nearest 100. And this is the answer we are looking for. That is, we want to show that the minimum time taken for a 0.50 kilowatt camping kettle to bring a cup of water at 20 degrees Celsius to boiling point is about 200 seconds, not exactly 200 seconds. Okay, from 200, and above, but we have to approximate this value to what? To the nearest 100. The noblest pleasure is the joy of understanding. Bye-bye.